Good afternoon, everyone. This is Kalyan Kumar from My Mathematics Association. I am happy to welcome you all to the second session of the second day of PMA Ramanujan lecture series. So today we have our distinguished speaker, Professor K. Srinivas from Institute of Mathematical Sciences, to deliver the lecture for us. So Professor Srinivas has been closely involved with our Pi Mathematics Association since our inception. He has been a key member in the development of our association. So I now request Dr. Yogesh of Pi Mathematics Association to formally introduce our distinguished speaker to the audience.
Very good morning to everyone. Hello, can you hear me?
Yeah, I can hear you.
A very good morning to everyone. It's my great pleasure to introduce the speaker of the day, Dr. Srinivas, Professor, H category from the Institute of Mathematical Science, CIT Campus, Tharamani. He has received his doctorate degree from the prestigious Invest Institute, TAFR, in the year 1995. His areas of research is analytical number theory, algebraic number theory, modular forms and elliptical curves, cryptography, and digital watermarking. He has published many research papers in the reputed journals. So far, he guided 3 research PhD students, as well as he guided more number of MSc and as well as MPhil students. He visited several reputed institutes all over the world: Queen's University, Canada, University of Turku, Finland, and I also visited Paris, the Department of Mathematics in Geneva, Rome, and also he is a member of with great academic institutions and societies, like member of Executive Council of Ramanujan Mathematics Society from 2010 to 2018. And he is a member of Board of Studies and various institutes like NIT Rukola, Central University of Tamil Nadu, and he is a co-managing editor of Hardy Ramanujan Journal. He also organized several international conferences and workshops in number theory, and he also a part of the a member of mathematics training and the talent search, that is MTTS program, since 1998. And also he is he loved giving more popular talks in mathematics, and also he delivered several talks on the mathematics of Ramanujan, and also he gave 2 programs on Ramanujan's works in Hindi as well as in English, which is broadcast by Air Delhi. So really is a great pleasure, sir, for being with us to give a lecture on this 133rd remembrance of the anniversary of the Ramanujans. I welcome you, sir.
Thank you very much.
Thank you,
Shall
sir.
we start? Yeah.
Yes, sir.
Can we start now? Yeah.
Yes,
Okay.
sir.
So I really thank the organizers of PMA for inviting me to give this talk, particularly Professor Sivaraman, who is a great friend of mine for a long time. Well, I'm very happy to see so many popular talks and with experts who are really working, in the area of Ramanujan. I congratulate Pi Mathematics Association for arranging such a wonderful, event. So My talk will be very focused one on a particular problem that Ramanujan was interested in. In fact, his first letter contains this problem as well. So let us see what is this. All right. So my talk is on lattice point problems. So what is a lattice point problem? So we are interested in counting points xy in the xy plane with integer coordinates x and y. So such points, they form a lattice in the xy plane, right? And therefore they are called lattice points. And then what is a lattice point problem? You count the number of points inside large closed domains. All right. That is precisely what is lattice point problem. So various types of closed bounded domains with nice smooth contours. So this is a lattice point problem in number theory. Okay. So classically, there are two problems which are well known. One is the circle problem of Gauss, which he asked in around 1800. Says how many points with integer coefficients are there, okay, inside a circle. All right. So that is called lattice point problem for the circle, or that is called the circle problem. All right. And the other one is asked by Dirichlet, which says how many lattice points are there inside a hyperbola, okay, and bounded by the axis and the hyperbola. Okay. So Ramanujan's lattice point problem comes, and on the other hand, Ramanujan in his first letter, he was interested in counting number of points inside lattice points inside a triangle. So we are interested in this problem, okay, lattice points inside a right angle triangle. So this is, basically what is lattice point problem. All right. So in this talk, we shall briefly touch upon the first two problems and discuss. Then later we will come to Ramanujan's lattice point. So circle problem of Gauss. Consider this circle. U square plus V square is equal to X. All right. And then estimate the number of integer points nm such that n square plus m square is less than or equal to x. So inside this circle. All right. So a natural way to estimate this. So remember, we are going to take x going to infinity. Therefore, the circles are large and large. And therefore, the problem is interesting and becomes difficult. All right. So the nice way is, to take a circle and split it into unit areas, all right, unit squares inside it, and to each square associate a lattice point, a point with integer coordinates. Since this is unit square, the number of points inside this, the number of points inside this will be like finding out the area of the unit squares, the sum of the union of the unit squares that are inscribed inside and also that contains this circle. That will roughly give you the number of lattice points that we want. Okay. So therefore, to each lattice point, we will associate a unit square. All right. Let's say to this point. Now, since I'm not using my iPad, so I'm not able to write it here. But to this, we fix up a particular unit square for each of them, for each lattice point. All right. So that is what we do. So to each lattice points P, which is let's say UI, VI, associate a unit square. All right. Now, the set of all lattice points is associated with union of all these squares. All right. So these squares are contained in the circle, in the larger circle. For example, there may be some lattice points which are inside, but the square is outside. So you take a larger circle like the red colored one. All right. Then the lattice points, the total number of lattice points inside this circle that we want to count is contained in the larger circle. On the other hand, the area of the smaller circle contains the lattice points inside the circle that we want to count. So what I'm saying is these squares are contained in the circle u square plus v square is equal to square root of x plus root 2, because root 2 is the diagonal of the unit square that you have in the end. And the union of these squares contain the circle, the smaller circle. All right. So therefore, the area of the circle is bounded by these two bounds, like pi r square, the area of the larger circle, and it contains, it's bigger than or equal to this area of the smaller circle. So here A is the number of lattice points that we are interested in. All right. So A is contained. So we have got a bound, upper bound and lower bound for the number of lattice points inside the circle. All right. In other words, A minus pi x, because when you open the square here, so you get a x term here and x term here. So therefore, A minus pi x is bounded by, you get some constants here, square root of x. In other words, we can write A is pi x plus O of square root of x. This O stands for saying that something is O of square root of x, means that this is less than or equal to some constant times square root of x, where the constant is absolute. Therefore, roughly saying, the number of lattice points inside a circle is about the area of the circle with an error term. This is the error term, O of square root of x. And O of square root of x is nothing but the perimeter of the circle, because 2 pi r, 2 pi square root of x. All right. So therefore, for a circle, we have seen the number of lattice points inside the circle is approximated by its area, and the error can be of the order of its perimeter. In general, if you take any closed, continuous, smooth curve, that means it should not have edges, pointed edges. The curve should be continuously differentiable, okay? And so if you take any smooth, continuous, closed curve, J with area, let's say F, and the perimeter or the length of the curve is L, then the lattice points inside this region is approximated by the area of the curve with an error of the order of the perimeter. This is in general true. This was proved by Stenhouse, and that we have seen by this simple example, like counting the lattice points inside the square. All right. You might have seen in Professor Bruceburns' talk that he also touched upon this problem, and therefore I have skipped many details here. I have cut short my talk because there's no point in repetition. He has given a very nice talk yesterday. So therefore, in general, you write it, Rx is the problem of counting the number of lattice points Nm inside the circle of radius square root of x. And one would like to, one knows by this elementary observation that Rx is given by the area of the circle, which is pi x, with some error. So as long as theta is less than 1, the result is non-trivial. All right. So the entire thing is, what is the error term? Okay. That is what is called the circle problem. Okay. So as we have seen, the previous exposition was by Gauss. It was around 1800, and he computed this theta to be half. Now Sierpinski later in 1906, he estimated this error term in a very non-trivial way, followed by Wander-Corput, which both of them showed that the theta can be less than or equal to 1/3. And their methods actually given birth to a new subject in number theory called exponential sum techniques. So the problems that the Gauss proposed led to various developments in number theory. And later, so 1/3 is like 0.3333, never ending. Landau, after a year, Landau, Littlewood, and Wolfish, they improved in the 3rd decimal place. So in analytic number theory, so even an improvement in the decimal places is considered to be a very big achievement. All right. Therefore, you see various people, they worked on it. Wolfish again, he improved to in the 2nd decimal place. Then in 28, Neelan, he improved in the 4th decimal place. Then Titchmarsh in 34, he improved in the 3rd decimal place. L.K. Hua in the 3rd decimal place. Cheng Jinren, a very, very famous Chinese mathematician, he got this one. And Novak, Kolesnik, Mojoki, and Martin Huxley, finally, the best known so far, is in the 2nd decimal, 0.3154 or 50. Okay, and then later he improved in 2003 to 0.3149. All right. So how far you can go down? All right. The problem is how far. What is the expected one? All right. So in this direction, Landau and Hardy, they independently showed that you cannot go beyond 1/4. You cannot go below 1/4. That means theta has to be at least 1/4. These are called omega results, okay, which means that there is a sequence of number x for which this error term, this one, is bigger than x to the power 1/4. All right, so you cannot have less than 1/4. In fact, K.S. Gangadharan in 1961, he showed that the error term is omega of x to the power 1/4 log x to the power 1/4 times log x to the power 1/4. So in analytic number theory, you will see so many logs. Okay, this is quite common in analytic number theory. All right, and the best known omega result is by Kannan Soundararajan, who showed that Rx is pi of x plus omega of x to the power 1/4 log x to the power 1/4 and this factor, all right, which is a ratio of 2 log and log x. So this is the best one. Okay. Now comes Dirichlet divisor problem. Okay. So this asks the following. So you are given a region uv less than or equal to x. So this is a hyperbola. Okay. Then the divisor problem is the estimation of dx, the number of points between the axis and the rectangular hyperbola, uv is equal to x. Counting those, if any, on hyperbola, but not on the axis. Because the axis contains infinitely many lattice points, so we leave the axis. All right? In other words, dx is nothing but integers mn less than or equal to x, 1. All right? This is same. These are different ways of writing the same thing. And in analytic number theory, one writes this dx as summation n less than or equal to x dn, where dn is the divisor function. The sum of the number of divisors of n is dn. Okay. So divisor function, the divisor problem asks for what is the error term when you compute dx. So what is the main term and what is the error term? Let's see. So this is the divisor problem. Dx is, the main term is x log x plus 2 gamma minus 1 times x plus error term. And this was Gauss who showed, Dirichlet who showed that it is in fact square root of x. In fact, this is very elementary to show that this is a square root of x. I think this is also Gauss, which has shown. I will come back to that. Okay. All right. So by definition, dx is nothing but summation n less than or equal to x dn, which is n less than or equal to x. This is a dn, d divides n1. So if you write n is equal to q times d, then you can write this summation as qd less than or equal to x. Sum is over q and d. All right. Now look at this picture. So this is q axis here. It is a d axis here. We want to count the number of lattice points inside this one. All right. So observe that the area under the hyperbola is symmetric with respect to the line q is equal to d. So this is the middle line, is the blue dotted line is q is equal to d. All right. And the graph is qd is equal to x, this one. Okay. So this hyperbola is symmetric about the line qd is equal to x. And now take any line, vertical line, this one. Q is equal to, let's say q is equal to square root of x, this one, this line. I hope you are able to see what I'm pointing out my arrow, cursor. So the area under this one, this area is same as the area of this up to this. All right. Therefore, if you want to count the area, entire area, you count any one up to this one 2 times, and then remove the area of the square because we have counted it twice. All right. So that is what we do. Let n1 be the number of lattice points to the left of the line q is equal to square root of d. Then the number of lattice points bounded by the hyperbola and the lines, the axis, is 2 times n1 minus the area of the square, small square, square root of x square. Okay, this one. All right. Therefore, 2 times x by q, this is the integral part of this. Because this is qd is x, bounded by qd is x. So if you fix any d, then the number of q's is x by d. Then run, or if you fix any q, the number of d's is x by q, and then you sum over all the q's from 1 to up to square root of x. This is what we do. So x by q, the total number. This is area of the thing to the left of the line x is equal to q is equal to square root of x minus the area of the square, small square that we have. Now this integral part, you can open it up. The integral part is the integer, the number plus the fractional part, and fractional part lies between 0 and 1, therefore it is bounded. So therefore this is nothing but x by q, there is a 2 missing here, so q is equal to 1 to square root of x, this one, minus square of this one, which is same as 2 times x. Actually x has come out here. Q is equal to 1 to square root of x, 1 by q plus o of square root of x, because there are square root of x terms. All right, each term will give you, there are some typos here. So this is, yeah, minus square this one and o of x square. So what you see here, 1 by q is equal to 1 to square root of x. Use the famous formula. The 1 by n is about log n, up to x is log x plus o of 1 by x. So using that one, we get this one sum up to square root of this up to this one, plus this is Euler constant, plus O of 1 by x, which is coming from the summing the first one. All right. And the second one gives you an x here. And then you have O of square root of x. Therefore, in total, what you get is 2x plus 2 gamma minus 1x plus O of square root of x. So this is the first approximation. And this was done by Dirichlet. Okay, alpha is equal to half. So Dirichlet divisor problem, if we write the main term as x log x plus 2 gamma minus 1 times x plus O of plus the error term, then our alpha is half. This is by Dirichlet. And then we have Vanderkarput again, who showed that it is 1 by 3. And then he improved it to in the second decimal place. Rickert and Tau, they improved in the third decimal place, and Kolesnik, and then Ivaniak and Mojoki, they 3181818, and finally Martin Huxley, he improved it to in the third decimal place in 1993, and again in 2003 3149. Again, the omega results were proved by Landau and Hardy. They showed that you cannot reduce this alpha below 1 by 4, this alpha here. So notice that the improvements for the divisor problem and improvements for the circle problems, they're more or less, they're same. All right. Why does that happen? All right. So a small remark. The circle problem and the divisor problem, they seek optimal error term in this. So Px is the error term in the circle problem, and let's say delta x is the error term in the divisor problem, and find the optimal Px and delta x. In fact, while evaluating this error term, evaluation of Px reduces to estimation of this exponential sums of this type. This R2n here is the number of representation of n as sum of two squares, all right, times e to the power 2 pi I square root of nx. And the evaluation of delta x reduces to finally showing that this particular exponential sum with a dn, e to the power 2 pi I square root of nx, is small in a certain sense. So you see here R2n and here dn, both of them behave in a similar way. Therefore, they the nature of analysis is same. Okay, and therefore you get similar results for both divisor and circle problem. So this is about a divisor and circle problem. Now we head to Ramanujan's lattice point problem. Okay, what is Ramanujan's lattice point problem? So Srinivas Ramanujan, as you have seen yesterday in Professor Bruce Bund's talk, the first letter contains several important results, and one of the entries is this one. In fact, Professor Bruce Bund's book, the last notebooks, they contain a very nice exposition of this, and another one is Hardy's book on Ramanujan, 12 lectures on the life and works of Ramanujan. So these are the references for this. So in his first letter to G.S. Hardy, Ramanujan writes, the numbers of the form 2 to the power u times 3 to the power v less than n is about log 2n times log 3n divided by 2 times log 2 log 3. All right, this is what it contains. That's all. I mean, this is one entry of the several entries. Now, how is it a lattice point problem? So look at this equation. So we want to count the u and v such that 2 to the power u, 3 to the power v is less than or equal to n. Take logarithm on both sides. So you get u log 2 plus v log 3 is less than or equal to log n. Okay. Now put omega as log 2 and omega prime as log 3 and eta as log n. Therefore, now we can rephrase Ramanujan assertion as finding the number of solutions of this inequality of u omega plus v omega prime less than or equal to n, the eta and bigger than 0, subjected to u is bigger than or equal to 0, v is bigger than 0. So count the number of solutions of this inequality. All right. And what Ramanujan said is that the number of solutions is eta square by 2 omega omega prime plus eta by 2 omega plus eta by 2 omega prime plus half. Of course, later it was pointed out by Hardy that half has no right to exist here. All right. So in any case, this half is not important here. So, but this main term is important. All right. So this is what Ramanujan's letter said. Okay. Now, let omega and omega prime be any positive numbers and write the number of solutions of this inequality u omega plus v omega prime less than or equal to eta, subjected to u is positive and v is positive. That means bigger than or equal to 0. What I mean is u is bigger than or equal to 0 and v is bigger than or equal to 0. So the number of integer points, these are nothing but counting the number of integer points inside a triangle which is bounded by axis and bounded by the hypotenuse eta. Right. So I have a picture for that, I suppose. Yeah, I will show you the picture later. All right. And by our previous analysis, the number of lattice points inside a right angled triangle with vertices this is nothing but area of the triangle plus order of the error is nothing but order of the perimeter of the triangle. Therefore, it should be like this: 1 by 2 times eta by omega times eta by omega prime plus O of eta. So this is, so you see the first term in the Ramanujan's thing, eta square by 2 times omega omega prime. So this one, okay, eta square by 2 times omega omega prime. So very good. Now notice that this the number of solutions of this inequality, they depend only on the ratio omega by omega prime, because number of solutions of n omega omega prime, or you multiply any number and any integer k time k to eta omega omega prime, the solutions don't change. Therefore, the first observation is the evaluation, the counting points, they depend only on the nature of omega by omega prime. So put this number omega by omega prime as theta. Right? Then Hardy, he showed that the number of solutions, lattice points, is this main term plus the error r eta, where r eta is given, is the nature of the bound r eta depends upon theta. So it is O of eta if theta is rational. So if omega by omega prime is a rational number, then your error term is O of eta. On the other hand, if theta is irrational, then this is little of eta. So little of eta means r eta divided by eta goes to 0 as eta goes to infinity. All right. Big O means r eta by eta is a bounded number as eta goes to 0, infinity. All right. And if theta is log 2 by log 3, then Hardy showed that this is little of eta by log eta. So this is what Hardy did on improved and analyzed the problem of Ramanujan. All right. By the way, Ramanujan gave a proof of this, the main term. All right. This is there in Bruce Burns' exposition. Later, Hardy and Littlewood, they studied it much closer, okay, further. And they said that, look at, let's say, theta is irrational, and look at the continued fraction expansion of theta, all right? Let's say Pm by Qm is mth convergent of theta. Now, if the Qm plus 1 grows like Qm to the power alpha naught for some alpha naught, then they showed that the error term R eta will be O of log eta provided alpha naught is 1. That means if Qm plus 1 is O of Qm, that means Qm plus 1 by Qm is bounded. So this partial, quotients are bounded, then this R eta is O of log eta. Otherwise, for all other cases, this is O of eta to the power 1 minus 1 by alpha naught plus epsilon. Okay? So it says that if this behaves like this, then this happens. All right. Okay. Then K. Ramchandra, Shankar Narayanan, myself, we made a remark at some point of time. This is a small remark, observation, which says that if you have theta is irrational, of course, but suppose this is quadratic irrational, okay, then R eta will be O of log eta. Sorry. Okay. And if theta is any other algebraic irrationality of degree bigger than or equal to 3, that means theta satisfies a polynomial of degree at least 3, then R eta is O of eta to the power epsilon. All right. And in the Ramanujan case, theta is log 2, which is like omega by omega prime is log 2 by log 3. Then we show that this alpha naught is equal to 2 to the power 40 log 3 is admissible. All right. Compare it with earlier one. So here, when partial quotients are bounded, you have log of eta. Otherwise, this one. So provided there exists some alpha naught. All right. So what we shown that if theta is any algebraic irrationality, then this is in fact O of eta to the power epsilon. And in the Ramanujan case, we have explicitly computed this constant, okay, alpha naught. All right. So much recently, Karthik Babu and Usha Sangle, they further improved this. They looked at various omega by omega primes, various ranges of omega by omega prime, and they improved on the constant. All right. So, for example, so this is a statement is pretty big. So let A be any positive integers such that A and B are multiplicatively independent. Put omega is log A, omega prime is log B, and theta is omega by omega prime. And let mu be an irrationality measure of theta. So irrationality measure means, see, there is a measure for every irrational numbers, how close they are to rational approximation. So look at all rational, if gamma, you say that mu is a rational irrationality measure of a real number gamma, provided mu is the infimum of all q to the power rho plus epsilon for sufficiently large q. All right. So take all expressions of the type gamma minus p by q, which is bounded away by 1 by q to the power rho plus epsilon, and take the infimum of all such rho. That is the irrationality measure. All right. In that case, you can say that this beta naught can be taken like this. There are various numbers that you have. In particular case of Ramanujan, they have shown that beta naught is in fact 2 to the power 18 times log 3. All right. So 2 to the power 40 has been reduced to 2 to the power 18. All right. Yeah, here is a very beautiful analysis which is done by Hardy of how to count non-trivially the number of points inside a rectangle. Remember, the trivial estimation is 1 by 2 times area, 1 by 2 times area plus of the order of the this thing is perimeter. Okay. Non-trivial, if you want to count, then what we do is take any line u is equal to n. Count the number of lattice points inside on the line u, and move u from here to 0 to up to this n by omega prime. All right, over all integer point, all the integer things. U is equal to 1, u is equal to 2, u is equal to up to u is equal to n by omega prime. That's what we do. Okay, so the line u is equal to n intersects the hypotenuse at the point this one. This is the point n, and eta minus n omega by omega prime. Therefore, the number of lattice points is nothing but the length of this one. All right, the integral part of this, which is 1 plus eta minus n omega by omega prime, the integral part of this, and then move line n from 1 to eta by omega prime. It should be n is omega prime. Okay, yeah, doesn't matter. Okay, so therefore, when we compute all these things, what we get, then remove the integral part of this. Yeah, we have also put this following things. So here, open up this one. Trivially, this is a integral part of x is nothing but x. What did we do? Yeah, x minus. So we are using this one, x minus integral part of. So the fractional part of x is x minus integral part of x minus half. So this is used because this has nice properties. This is periodic function with period 1, and it's very helpful in the analysis of this kind of problems. So once you do all these things, then you get this sum, n is less than or equal to eta by omega, this sum, first sum minus this one. And the first sum here is evaluated in a trivial way, and the second sum is evaluated in the non-trivial way. So you look at the first sum. The first sum is, if you look at this one, so n is up to this one. Therefore, you get eta by omega integral part of this plus 1 times this one. So this is quite easy, just straightforward. And that gives us that this is eta square by 2 times omega prime plus 2 eta by 2 omega plus eta by 2 omega prime plus a bounded number. Therefore, in essential, this thing reduces to this is the main term that we get, and this is the error minus s eta. All right, and the entire thing is to compute s eta. So what is s eta? All right, that is the main thing. So Hardy proved that s eta is nothing but eta by qm it's bounded by O of eta by Qm plus O of Qm. So what is here Qm? Because theta is irrational, look at the convergence, Pm by Qm. So here Qm denotes the mth convergent, the denominator of the continued fraction for theta. So this is where the approximation, the continued fraction approximation of theta is used, okay? And this is slightly non-trivial, so I am skipping the details of this one, how he got it, but it is there in Hardy's book, 12 lectures on the life of Ramanujan, all right? So once you have this one, the S eta is bounded by O of eta by Qm plus O of Qm, then this is known that given any positive delta and sufficiently large eta, you can always find an m such that this Qm, this number Qm is bounded by eta, delta times eta, and it is bounded below by 1 by delta, all right? So once you have this one, once you know this one, then eta by Qm, the first term here, from here, so if you multiply here eta both sides, so eta by delta is less than eta times Qm, or eta by Qm is less than delta. So eta by Qm is less than delta times eta, and Qm is less than delta times eta. Therefore, the sum will be less than 2 times delta times eta. And therefore, this S eta, the error that we had, this is little of eta. So this is how Hardy obtained his, Hardy showed this little of eta for all irrational theta. This is how. All right. All right. Yeah. Then what further has been done? Now, so our observation is a very elementary observation, of course. Now, Qm plus 1 in the Hardy-Littlewood's proof, you see Qm plus 1 should be bounded by Qm to the power alpha naught for some alpha naught. So notice that if you look at theta minus Pm by Qm, where Pm by Qm is any mth convergent for theta, then it is bounded by 1 by Qm into Qm plus 1, which implies that this Qm plus 1 is bounded by 1 by Qm theta minus Pm, the absolute value of this. Therefore, you need a lower bound for absolute value of Qm theta minus Pm of the type bigger than Qm to the power alpha naught in order to apply Hardy-Littlewood's idea. All right, because then Qm plus 1 is bounded above by Qm to the power alpha will come. So, but this result is, true for if theta is a quadratic irrational, then the partial quotients are bounded, and therefore alpha naught is equal to 1, and thus R eta is O of log n, or log eta. So this is true for all algebraic irrationals of degree 2. All right. On the other hand, if theta is any algebraic irrational of degree at least 3, then it is known by Roth's theorem that alpha naught can be taken to be any constant bigger than 1. And therefore, again from this analysis, it follows that R eta is O of eta to the power epsilon. All right. Now, in the special case of Ramanujan, when omega by omega prime is log 2 by log 3, there is a very nice result by Feldman and Baker and Westphal, who uses linear forms in logarithms. And by following their method, one can explicitly show that alpha naught is 2 to the power 40 log 3 is admissible. All right. Therefore, in this expression, R eta as eta to the power 1 minus 1 by alpha naught plus epsilon you can take this alpha naught to be 2 to the power 40 times log 3, where epsilon is positive. Now, in the results of recent results by Karthik and Usha, they use a result of Goulion and the concept of irrationality measure of theta and compute the exponents alpha naught for various values of omega and omega prime. All right. So they use, again, a recent result. This is a recent result of Goulion, which gives you the lower bound for linear forms in logarithms. All right. This is a result on linear forms in logarithms. So therefore, they get a better constant than what we have got here. And as a byproduct, they improve on several ranges of omega by omega prime. In particular, in the case of Ramanujan, they get this constant 2 to the power 18. So you see, I mean, the object of my is that I didn't want to touch upon other areas in today's talk, because already Professor Bruce Point has given talk, Professor Ramamurthy has given a talk on Ramanujan's, and Professor Binua has given, and also, you know, we are going to have 2 more things. So we have, it's a very nice opportunity to get exposed to the kind of mathematics that Ramanujan did. And this is one part where, you know, I think you may not have seen the exposition before, and therefore I wanted to only touch upon this one. So I think I will stop my presentation here. In case if you have any questions and all these things, I would be happy to address. Thank you very much.
Thank you very much, sir, for discussing in detail about Ramanujan's lattice point problem and other related topics. So we will definitely go through your material in addition to Professor Bruce Burns' material yesterday to gain an understanding of these topics. We really thank you for that. So I now use this opportunity to request the students and participants to raise their doubts and clarifications. So our professor will be eager to answer those with this and enrich us with his knowledge. Students, please type your questions in the comment section so that it will be visible to professor and other participants. Vijay Kumar sir, do we see any questions from students?
Not yet, Kalyan.
Sivaraman sir, do you have any questions from your end, sir?
I don't have as of now. I don't have any questions.
Yeah, actually, this is you know, see, as Professor Bruce Byrne commented yesterday about Dyson's remark. So whenever you are getting headache or you know, or not well, one should get into Ramanujan's notebook for relief. All right. So, in fact, you know, people like Bruce Byrne, Andrews, Krishnaswamy Alladi, Ramamurthy, Kumar Murthy, Soundararajan, Manjul Bhargava, you know, they have brought out Aken Ono. There are many names. I'm missing many names. Okay. So now they're unraveling the beauty, you know, which Ramanujan left for us. All right. So it's so nice, and you know, I mean, to know, you know, what kind of things Ramanujan has thought, how much ahead of time he was. All right. And how much he left for us, you know, for, you know, to kind of enjoy and see the beauty. So I request, you know, students sometimes, you know, go to library or look in the internet, look at the papers, recent papers on the work of Ramanujan for inspiration. It's a very beautiful thing.
Yes, sir. So that is a very useful advice for students during this occasion of Ramanujan's birth anniversary. So I now request Mr. Nagaprasadu of our association to deliver vote of thanks to our distinguished speaker.
Before Nag Prasadu takes over, I would also recommend students to go through the book written by Professor Sivaraman. Okay, it's a wonderful book on Ramanujan, written in Tamil. In fact, I have got it reviewed by many people who said that this should be translated into English. So nothing, a better comment cannot be there better than this. That is the appreciation that this book has.
Thank you, sir.
So yeah, so one should look into the works that Sivaraman has done. Okay, that's also a very good source of inspiration. Yeah, thank you.
Thank you very much, sir. It's actually an honor for me to give a vote of thanks for your lecture, and I am privileged to do so. So, first of all, we will like to extend our hearty thanks for you taking this opportunity to give a lecture on association. I mean, on behalf of our association for the 133rd celebration of Ramanujan's birthday by Mathematics Association. So we thank you very much for the lecture on the lattice point problem, specifically by Ramanujan, because it's the celebration of Ramanujan's birth anniversary, 133rd anniversary, and having this problem discussed. And also happy to see that you are also have done some analysis and have provided some observations, which is very much significant. And I'm very, very happy and proud to know that you have also given some contribution to the problem that has been defined by Ramanujan. And also, there have been observations by Hardy. So, tiny drops makes the ocean, sir. So, I mean, this is one of the tiny drop of your contributions, and there are plenty more on number theory. The people who have been mentoring on cryptography as well, on some of the people whom you have been mentoring on your contributions to cryptography, or plenty of other applications with respect to number theory. So we are happy and glad to have your lecture on this day, and I think it will be very much useful to the students to explore further on the lattice point problem by Ramanujan and the observations provided by the professors. So we thank you very much for the wonderful talk on the same. I thank Sivaraman sir for this opportunity, as well as the organizers for having this wonderful session in mid of this pandemic, so that it will be very much useful and then encouraging for the students to go further. And also, we are very happy to hear from you that you have asked some of the professors and well-known people of yours to go through the book written by our beloved Professor Sivaraman sir on Ramanujan's life, and the comment being that it can be rewritten in English is a I mean,
sure,
it's something which we can't even admit. So that's the kind of dedication our professor has, Sivaraman sir, and we are happy to have him as our professor. And thank you very much for the same, Sivaraman sir. And I also thank all the organizers and the students for being having part of this live stream. And this will be available on YouTube, and the people can see whenever they want to have and understand about lattice point problem. Thank you all for the opportunity.
So just two lines before closing up. Nagaprasadu was gold medalist at Anna University. He did his MSc Mathematics, and he did his project under Professor Srinivas. So he knew Srinivas more.
Yeah, we have long association.
Yes, so that's one thing. So that's the reason why we have chosen him for this session.
I was lucky to have Nag Prasad as my student.
Sorry, sir. I am lucky to have you as my mentor, as well as
both
sir as my long-time mentor. No need to mention.
Okay, and we are lucky to have process like Srinivas who always help our association. I have to, as a founder, I have to register my sincere thanks to Professor Srinivas, who always have been helping us right from the inception, even before the inception. I could remember that he was one among the speaker at our first book release. Until today, he was obliging to all our requests. Whenever possible, he comes voluntarily and help us. And this kind of attitude will motivate our association to grow more. Our sincere thanks to you, sir.
Thank you very much, Sivaraman, and all the members of PMA. You are doing a very good job. Thank you very much.
Thank you, sir.
So thank you, Mr.